Welcome, everyone. Today, we're diving into Chapter 6, Ethical Design and Development. And honestly, this is where the conversation about generative AI gets really interesting. Because we move beyond asking, can we build it? And start asking, how should we build it? Our focus is Gen AI in cybersecurity, where the stakes can be incredibly high. A system may influence which activity gets flagged, who gets investigated, what data is exposed, or how quickly an organization responds to a threat. So fairness, transparency, security, and accountability cannot be optional extras. Here's the big idea I want us to carry through the presentation. Ethical design is not a checklist we attach at the end. It is a way of operating from the first conversation through deployment and continuous improvement. We're going to turn principles into practical controls, things teams can actually design, test, document, monitor, and improve. So, let's jump in and see what responsible Gen AI looks like when ethics becomes part of the engineering work itself. Let's start with the full life cycle, because this picture gives us the backbone for everything that follows. At the define stage, we bring in stakeholders and set clear purpose boundaries. Then, during the build stage, we make intentional choices about data and privacy. Testing is not just about accuracy. We also test for bias, adversarial manipulation, and unexpected behavior. Before deployment, users need understandable explanations and meaningful human oversight. And once the system is operating, the work absolutely does not stop. We monitor outcomes, collect feedback, provide redress, and adapt. Now, notice the shift here. Ethics is a design input, not a final approval stamp. Every important decision should leave an evidence trail. Documentation, test results, risk decisions, and named owners. And here's the exciting part. When we treat Gen AI as a living system, it can improve as threats, users, and social expectations change. The life cycle becomes a continuous learning loop rather than a straight line to launch. So, who needs to be in the room? The short answer is more than just the technical team. End users bring the reality of the workflow. They can tell us where a system might create friction, misunderstand context, or cause harm. Ethicists help surface value conflicts and challenge assumptions that may otherwise stay invisible. Legal experts translate rights, duties, and regulations into concrete requirements. And technologists turn all of those insights into architecture, controls, tests, and operational safeguards. What I love about this model is that each group catches a different kind of blind spot. An AI recruitment tool, for example, might be technically impressive and still reinforce discrimination if the people affected by it were never involved in the design. And one more thing, ethical capability needs continuous training. Different roles need different scenarios, practical cases, and regular opportunities to test their judgment. Ethics is not one annual module. It is shared professional practice. Learned together, applied repeatedly, and strengthened through honest discussion. Trust sounds abstract, but this slide breaks it into 3 very practical layers. First, transparency asks, what can we see? That includes the data sources, design choices, decision logic, limitations, and documentation. Second, explainability asks, why did the system produce this particular output? The explanation has to make sense to a human in context, not just to the engineers who built the model. Techniques like LIME and SHAP can help, but the real goal is useful understanding. Then we reach accountability. Who acts when something goes wrong? This is where named owners, audit trails, incident reporting, investigation, correction, and redress become essential. And here's the key pause. Transparency alone is not enough. We can expose a huge amount of technical information and still leave people confused or powerless. These 3 layers work together. They make a decision inspectable, understandable, and contestable. That combination is what allows users, operators, and regulators to place justified trust in the system. This slide gives us a simple but powerful data discipline. Collect less, protect by design, and use data only for the declared purpose. First, collect less. If the system does not genuinely need a piece of personal data, do not collect it. The data we do use should be representative, responsibly sourced, and supported by consent and clear provenance. Second, protect by design. That means anonymization where appropriate, encryption in transit and at rest, access controls, and regular privacy audits. Privacy is strongest when it shapes the architecture from day one, not when it is patched in after a problem. Third, keep the use tightly connected to the stated purpose, and this is where function creep becomes a major concern. A threat detection system may start with a legitimate security goal and slowly become an employee surveillance tool. So, pause on this idea. Purpose limitation is not only a privacy principle, it is also a security and trust control. Clear boundaries reduce misuse, clarify accountability, and help everyone understand what the system is and is not allowed to do. Now we're moving into robustness and security, and the main message is that secure AI is an operating practice, not a launch checkpoint. We begin by threat modeling the AI system itself. Could an attacker manipulate inputs, poison the training data, abuse the model for an unintended purpose? Then we harden the environment with secure training practices, encryption, and controlled access. Next comes stress testing. This is where edge cases, failure modes, and ethical hackers become incredibly valuable. We want to discover weaknesses before an attacker or an innocent user does. Finally, we audit and update continuously because both AI behavior and cyber threats evolve. On the right, we also have the compliance baseline, data protection, consent, sector obligations, risk-based requirements, and ongoing legal expertise. But here's the important distinction. Compliance can tell us whether required controls exist. It does not automatically prove that the system is secure. Strong teams connect legal obligations with technical evidence, real-world testing, monitoring, and rapid adaptation. Bias is often discussed as if it were one generic flaw. This table shows why that is too simple and why diagnosis matters. Skewed training data can disadvantage underrepresented groups, so the response is more diverse and representative data. Flawed algorithm design can place too much weight on problematic proxies, which means fairness has to be designed and tested explicitly. A model can also be applied outside the context where it was validated, causing error rates to rise. Historical data may reproduce past discrimination, and a development team without diverse perspectives may simply fail to notice unfair behavior. The interesting part is that each source requires a different response. More data will not fix every algorithmic design problem, and a technical adjustment will not automatically repair a harmful deployment context. So the mindset is, identify the source, choose the matching intervention, and check the outcome again. Fairness depends on recurring audits, transparent criteria, user feedback, diverse teams, and legal compliance. It is an ongoing quality discipline, not a one-time dataset check. Here's a question that can completely change a design conversation. The system works, but works for whom? Technical accuracy matters, of course, but a responsible system must also support human well-being, respect rights and privacy, remain accessible to diverse users, and preserve meaningful human agency. In cybersecurity, that might mean protecting people from cyberbullying without creating excessive surveillance. It could mean designing an interface that works for people with different abilities and levels of technical expertise. And it definitely means allowing qualified experts to override or adjust an AI decision when context or human judgment demands it. Culture matters too. language, norms, expectations, and legal requirements vary across communities and regions. A system that feels appropriate in one setting may be confusing or harmful in another. That is why interdisciplinary research is so valuable. Computer science needs to connect with ethics, law, sociology, HCI, economics, and domain expertise. When those perspectives collaborate, works becomes a richer standard. Not merely functional, but useful, inclusive, respectful, and genuinely beneficial. This is where ethics becomes dynamic. A feedback mechanism lets the system learn from consequences that were impossible to predict perfectly during development. The process starts by defining ethical guidelines with diverse stakeholders. Those principles are then integrated into the design. Next, the team creates real feedback channels for users, employees, and external experts. After deployment, the system is monitored continuously. Feedback is analyzed, root causes are identified, improvements are made, and the organization reports progress while reinforcing an ethical culture. And notice the two supporting practices at the bottom. Impact assessment asks, what risks and effects are appearing for users and society? Continuous monitoring asks, is the model drifting? Are threats changing? Are users raising new concerns? And are the controls still working? Here's what makes this exciting. Feedback turns ethics from a static document into a living control system. The goal is not to promise perfection. The goal is to notice problems early, respond transparently, learn quickly, and keep the technology aligned with human values as the environment changes. Let's bring everything together with 3 practical design gates. Before build, define the purpose and prohibited uses. Engage end users, ethicists, legal experts, and technical specialists. Document data provenance and consent, and agree on fairness, privacy, and security criteria before implementation begins. Before deploy, make sure decisions and limitations can be explained. Run bias, privacy, impact, and security tests. Assign clear owners, escalation paths, and redress mechanisms. And confirm that the system is accessible and supports human override where needed. Then, in operation, monitor drift, threats, and real-world outcomes. Keep collecting feedback. Audit the controls. Update the model and report incidents, changes, and lessons learned. So, here's the takeaway I'd love everyone to remember. Responsible Gen AI is not simply a compliant model. It is a monitored socio-technical system. It includes people, processes, data, technology, governance, and continuous learning. If we build those elements together from the start, Gen AI can strengthen cybersecurity while also earning the trust of the people it is meant to protect.